Hello again, students. We're continuing with the notes on Chapter 5, Newton's Laws, and we're going to do some more examples of how to use Newton's second law. So take a look at the question here. It says, a toy rocket of mass 0.25 kilograms has an acceleration of 50 meters per second squared. What is the thrust of the engine? Ignore gravity. Okay, so how are we going to do this? We're going to first identify what we know, the givens. So let's see here. We've got 0.25 kilograms. Okay, that's going to be the mass. And we're given here 50 meters per second squared. That's the acceleration. And the thrust is the force of the engine. So the force, technically we should say the net force, is the thing that we do not know. So I'll put a question mark next to that. And okay, so what we're going to do is we're going to do F net equals MA equals, and then we're going to plug in the number for the mass, plug in the number for the acceleration, and do that on a calculator and get the answer. Now, I'd like to point out to you that a couple of pages down in your notes, you're going to find the solutions to these questions. All right, but anyhow, let's move on. Now, once again, I think we mentioned this before, but the G's, the number of G's is defined to be the force caused by the acceleration divided by the weight, right, over the weight. That's one way. Or more straightforward would be to just say it's the acceleration over G. And so whatever the answer was, okay, well, here we're given the acceleration, so we could put in 50 meters per second squared and divide by 9.8 meters per second squared, and whatever that is, that's going to be the number of G's. Okay. All right. Let's take a look at number 2. How would we figure out the mass of a horse? We're given the weight. Well, all right, so the simplest way is to start off with, first of all, identifying the, we've got here the weight. I'll label this F sub G for weight. And the question is, what is the mass? So here the question is, what is the mass? All right, so we've got F sub G, the weight, is equal to the mass of the object, in this case the horse, times G. We're going to solve for the mass, and so we get mass equals F sub G over G. And so we're going to put in here 14700 newtons over 9.8 newtons per kilogram. So newtons per kilogram is the same thing as meters per second squared. And the newtons are going to cancel. You're going to have units of kilograms, and that'll get us the answer. You can check later on. All right. Let's take a look at the third example. Naughty Peter's spitball weighs 1 gram. Okay, so one thing we need to do is to see, this is a mass, all right? So we're going to convert. Mass equals 0.001 kilograms. The question continues, what is its acceleration as it travels down the disgusting straw with 0.3 newtons of hot air pushing on it? All right, so we've got here the net force, F net. And so what we're going to do here is what is it asking? Oh, it's asking for A. So A equals what? All right, well, Newton's second law. A equals F over M, net force, over the mass. And so we're going to put in the 0.3 newtons. We're going to put in the 0.001 kilograms and get the answer. Okay. Let's keep going. Number 4. Okay, now this one's going to get a little more complicated. The first rocket one, remember it said ignore, it said ignore gravity. Well, right here it said ignore gravity. Okay, but now we're not going to ignore gravity for this new problem. Let's go down here. Okay, so let's see. This time, the thrust is only 3 newtons. And, all right, okay, so the multi-part problem, what is its weight? So it's asking, what is the force of gravity? So we're going to write down F sub G equals mg, which is going to be 0.25 kilograms. And so let's see here. Oh, let's see. We need to multiply that by G. 9.8 newtons per kilogram. And we're going to get, what I need is my calculator. Let me interrupt this while I get my calculator out. Okay, so I'm back. What I decided to do is bring up the terminal, and basically all computers have now a terminal, and then basically all computers have something called Python loaded on them. So I started up Python, and I can put in simple math problems here. So 0.25 times 9.8 is 2.45 newtons. So, all right. So, I want to just hide the window. Okay, so, yeah, we have that. The answer is, now I already forgot. What did I say it was? It's 2.45 newtons. All right, back to here. So 2.45 newtons. So F sub G equals 2.45 newtons. Now, the next question is, what's the net force on the rocket as it flies vertically? Well, the net force is the sum of all the individual forces. There are only 2 of them right now. So we've got the F of the thrust plus the weight, and F sub G. And that's going to be 3 newtons in the upward direction. But now the thing is, the weight is a downward force, so it's negative 2.45 newtons. And so, okay, so that means it's going to work out to be altogether 3 minus 2.45, that's 0.55, 0.555 newtons. Okay, so yeah, things got a little more complicated. Gravity is slowing down the rocket while the rocket engine is pushing upward. They're kind of working against each other. The fact that this is positive means the rocket's engine is a little bit stronger than the gravity, and so yes, the rocket is accelerating upward. And the acceleration is the net force over the mass, which is going to be the 0.55 over whatever 0.25. So this is newtons, and this is kilograms. You do the math, and you're going to get the answer in meters per second squared. Okay, so let's see, how are we doing here? And okay, so here are the solutions. You can see how to do the problems there. Okay, so let's keep going a little bit. Let's talk about combinations of forces. So the previous problem actually was a combination of force, but it was a simple one because they were kind of lined up. The weight was straight down and the rocket was going straight up. But sometimes things get a little more complicated, like we have a rocket that's going off at a slant. Okay, so let's just see here. Now, when you have things that are not pointing in the same direction, it's really helpful to use the I and J and maybe even K vectors as a way to kind of keep track of what's the horizontal component, what's the vertical component. So we'll take this approach on this example. So I've got a rocket of mass 100 kilograms, and its thrust is 2,000 newtons, and it's flying at an angle of 10 degrees relative to vertical. Now, one thing I need to tell you right away, I know that we're kind of used to thinking of the coordinate system for the angles as relative to the horizontal or the x direction, and then having the angle be this angle here. But very often, this is not the way the problem is stated. Now, you have an option here. You could say, okay, well, if this is 10 degrees, then this must be 90 minus 10, which would be 80 degrees. That's one way to do it. And, you know, that's an option. You can do that. But the other way is just to just keep track of the fact that, yeah, now we're doing things relative to the vertical axis. So anyhow, let's what we're going to do in order to combine the force of the rocket engine with the weight force, we need to decompose this force vector here. We need to decompose it into a vertical and horizontal part. So I'm redrawing, here's the original thrust vector, and we're decomposing it into the y part and the x part here. I'm going to erase this. Okay, so now if you look at this triangle, you see this is the opposite side. The x part is the opposite side. This is the hypotenuse, and the sine of this angle is the opposite over the hypotenuse. So we can say that the x part of the thrust is the sine of 10 degrees times the hypotenuse here. And so that's how we get the 2,000 times the sine of 10 degrees. And then since it's times the horizontal unit vector, that takes care of the horizontal piece of it. Now, here I say plus, and then we need the vertical part of it, because here's the vertical unit vector. Well, this here is the adjacent part of the triangle, and this is the hypotenuse. Cosine is the adjacent over the hypotenuse. So the y part here is the cosine of 10 degrees times the hypotenuse times 2,000. Okay, so now we have the x and y components for the thrust. For the weight, it's going to be 100 kilograms times 9.8, g is 9.8, and so we get 980 newtons in the negative j, or the negative up direction. So in other words, it's a down direction. That's what the negative sign means. Now, when you combine vectors, you need to, when you're adding them up, you need to add the I coefficients, and then you're going to add the j coefficients, but you do them separately. So okay, so here let's go for the I coefficients. So here is the x coefficient, the x part of the thrust. The gravity had no x part, right? That's what this 0 meant, right? No x part. Okay, so 2,000 times the sine of 10 degrees, that gets me the 347. Right? That takes care of the x components. Now for the y components. So we have 2,000 times the cosine of 10 degrees. That's part of it. And then we have the weight, right? The weight, the minus 980. Oh, there it is. So it's 1969.6 minus 980. And that gets us the y part of the answer. And then the 347, that's the x part of the answer. All right. So, when I was grading the quizzes, I saw a lot of people making the mistake of not keeping the I hat coefficients separate from the j hat coefficients. You don't want to mix them up. And so that's what we're doing here. We're being careful. We're not mixing them up. All right, so let's see what we have now. We figured out what the force is on the rocket. And, okay, so, now, you could say we've got the answer. But very often in a test or in a homework problem, the book or me or whatever will say, well, I don't want the answer in this form. I want to know the magnitude and the direction of this force. So that means you got more work to do. Okay, so how do we do that? Well, the magnitude is easy, right? It's going to be Pythagorean theorem. It's going to be this, the x part squared, plus the y part squared. And that is exactly what's happening here. X part squared plus y part squared. Take the square root of all that, you get the answer, the magnitude of the net force. Now what about the direction? Well, so the direction is going to be found by, you need to diagram this, really. So the I part is positive, the j part is positive, and so we know that the answer vector is going up and to the right. And then, okay, so now this is the vertical component here, and this is the horizontal component. So in this triangle, the horizontal component is 347, the vertical component is 99.6, and this is a right triangle, so the tangent, which is the opposite over the adjacent, can be used. So the tangent of this angle is going to get you, is going to be given by this and that. But what we're after is the angle itself, right? So we want the inverse tangent or arc tangent. And now here's a place where you're going to make mistakes in quizzes. Remember that I told you we're not using a coordinate system like this. We're this particular problem, you can say, oh, I don't like this problem, and I would agree if this is nasty. It's not using this angle, it's using the other angle. So if it were using this angle, it would be arctangent of the y part over the x part. But since we are using this angle, it's the other way. It's the arctangent of the x part over the y part. Anyhow, you go ahead and plug in the x part and the y part, and you put this into the calculator. Don't forget to be in degrees mode, not radians, and you get your answer. Voila. And finally, if I happen to ask you, what's the acceleration? Well, you would get the net force. To find the acceleration, you'd use the magnitude of the net force and divide by the mass, and you would get the answer. That would be the magnitude of the acceleration, and the direction would still be the 19.3 degrees. Now, in a homework problem, you might want to be careful, on this test also. You might want to say, this angle is 19.3 degrees to the right or east of, but anyway, in this case it's up and down, left and right. So to the right of the vertical axis, or something like that. You need it, because oftentimes you might not know, relative to what, so you need to say that.